Hi, my name is Bailey Chambliss, and this is my Physics 2211 Lab Number 2, Motion of a Falling Object. So the purpose of this lab is to observe the motion of an object that is dropped from rest to moving straight down. We also analyze the effect of a drag force on an object's velocity and the significance of terminal velocity. So an analysis would be that I recorded a tennis ball falling off of a desk and onto the ground and analyzed that video using the tracker software. Using Python, I then created two simulations of the situation, one taking only into account the gravitational force and then the other taking into account both the drag force and the gravitational force. So this was an exploration of Newton's second law, which is represented as the force is equal to mass times acceleration. So a brief summary of our results: Newton's second law, F equals ma, where a equals negative 9.8 meters per second squared in the y direction, applies to objects in free fall experiencing no frictional forces. The model simulated under perfect conditions, which was our glow script or Python models, differed from the tracker model slightly because the simulation occurred in the real world and not under these perfect conditions. So the scientific principles in this experiment are Newton's second law, which is F net equals dp dt. The velocity update formula, which is that the final velocity of an object is equal to its initial velocity plus the net forces divided by its mass times the change in time. Then our position update formula, which is that our final position is equal to our initial position plus the average velocity times the change in time. Then our gravitational force is Fg equals negative mg, where g equals negative 9.8 meters per second squared in the y direction. And then our net force, which is that our net force is equal to the force of gravity plus the drag force. In the diagram on the right, you can see that the drag force is pushing the object in the positive y direction, while the force of gravity is pulling it down in the negative y direction, and our net force is the sum of these two forces. So we begin with our tracker model, where our system is the tennis ball, our surroundings are everything else, and our tennis ball begins approximately 0.8 meters above the ground. So next, we have our glow script model of the situation, where we took our initial conditions from the tracker model and put them into glow script so that it would give us a representation of what this would look like under perfect conditions. So our initial position is approximately 8.8 meters above the ground, and our initial velocity is 0, and then our time is 0.434 seconds. So next we did the same thing, but this time we took into consideration the drag force. So our initial position, velocity, and times are the same, but we just added in another force, which is drag. So in this diagram, you can see our position versus time graph of our tracker versus our Python models, and there are some slight differences, but overall they do follow the same kind of direction, which means that our actual situation, although not perfect, is headed in the right direction. So in conclusion, Newton's second law describes the relationship between acceleration of an object using force applied to the object and the mass of the object. The greater the downward force, the faster the object will accelerate. However, an upward force such as drag, in this case air resistance, opposes this, making the object move slightly slower. Some sources of error in this can be human error, which can come from incorrect points on tracker, incorrect massing of the object, and incorrect measurement of the height of the table. So some discussion questions: which model, if any, predicts terminal velocity? The glow script model that takes into consideration both gravity and the drag force would most likely predict terminal velocity. The force of drag is what prevents an object in free fall from accelerating without bound. Because of drag, there reaches a point where a velocity higher in magnitude is unattainable. This is when we see the graph of the velocity versus time graph beginning to flatten. So what if the object was thrown downward instead of dropped? In this case, the terminal velocity would still be the same. The object would just reach this point quicker. Graphically, this would be represented as a steeper slope, and the graph of the function of velocity versus time. Thank you.